Okay, welcome to the second lecture, which is about backward proofs. So I'm going to explain what that means, and about tactics. Tactics is Lean's way of supporting backward proofs. So let's look. I hope my whiteboard is good enough. Yeah, it's not optimal, but you can read it. So we have three assumptions here, or lemmas here. One is just A implies B implies C, and we want to prove C. First, what would a forward proof look like? And maybe the forward one is more natural. Well, a forward proof would start with A. And we say we have A. And then what else can we derive? Well, from A and A implies B, we derive B, right? Oh, let's use the whiteboard. So we derive B. And then, well, this is not ideal, but we'll live with it. And then with B, we can plug it in here, and then we obtain C, like this, right? Which is our goal. This is what we wanted to prove, and we've succeeded. So this is a forward proof. We started at the top, and we went downwards. So forward also means downwards, if you like, from what we know towards what we want to prove or conjecture. Forward proofs probably feel quite natural. This is probably, if I ask in class the student, oh, please prove this, they would probably have gone for the forward proof spontaneously. But in theorem proving, we find the backward proofs is often more convenient. And we'll see why, because we'll learn both styles, and then you'll decide yourself which of the two styles you want to use in the exercises and the homework. But in my experience, almost everybody uses backward proofs almost all of the time, at least among students. Okay, so what is the backward proofs? Well, the backward proofs would start with C, and we would say, oh, we want to prove C. What can help us prove C? Well, this formula here can help us prove C, because this one says, hey, I can prove C as long as you give me B, right? So this C and this C here match. But then we continue, we form a chain, but from the bottom, we match those two together. We see, well, we just need a B now. And we look, who could give us a B? Well, that's obvious. This one here gives us a B. But this one gives us a B at the cost of an A, right? Which happens to be there. And then we've won, right? So this is really like, imagine you're in a village in the middle age and you don't even have money, right? But you have different produces like, oh, I've got some chicken, I've got some vegetables, and so on, and keep on going. I'll give you vegetables and you give me fruit, and then you get all the way up here doing these kind of exchanges. And this is basically what happens if you like metaphors. And if you don't like metaphors, I suggest you change channels, because I like metaphors. So jokes aside, this is the backward style, and this is what I'm going to teach now. In Lean, of course. But I mean, we're using Lean as a vehicle, but all these concepts also exist in most other proof assistants. So Coq, Isabelle, PVS, and so on. Pretty much all except Agda has a concept of backward proofs and tactics. So we can go a long way with these concepts. Okay. So in the file, we have the usual boilerplate at the beginning that we don't understand or care about. And I'm going to start, explaining what is the tactic mode, and especially what are the basic tactics, because tactic modes with no tactics doesn't bring us very far. So tactic mode is, previously here we would have entered a sorry like this. We would have said, we've stated the property, we've stated the lemma, we are done, sorry, we have no proof. And now, in the second lecture, we're already going to see how to write these proofs, right? And this is really the video game aspect of theorem proving, filling out those gaps where you know the properties you want to prove, but you have to write the proofs. Okay, and here, well, this is too early. We cannot parse this, but this is a proof. This is a property that says for all properties A and B, for all propositions, so for all Booleans, if you like. So if A implies I mean, this you can see as A and B implies A. So A implies B implies A. It's a bit like currying from functional programming, right? So A and B implies A, right? And well, actually, I can already walk through the proof just to give you the flavor of it, but I will explain all of this in more detail below. So at first, our goal is shown here. This is what we have to prove, right? This is what we had below the line here. But as we went up, the goal changed. At some point, B was the goal. At some point, A was the goal, right? Well, Lean keeps track of this much better than this whiteboard, right? And much more reliably. So we're in good shape. So we start here, and it's very important to put the cursor at the right place. So here is, you see before the command, so that means we're at the very beginning, and the goal just reproduces what we have on top here. And it's very useful to have the lean info thingy here at the bottom, right? So if you have lost it, then I think you have to press this button, then it pops up at the wrong place, and then you have to carefully move it to where you want it. That's, you know, takes a couple of weeks of practice, and then you'll do that right. This is maybe the most difficult aspect of the whole course, if you ask me. So, okay, then we apply this command. So we go at the comma after the command. It's a list, right? It's begin, then you have a list of commands. And then you see intros AB, moved AB into the context. And then we just have to prove this. So in the context, that means they're now kind of assumptions, or they're kind of fixed, right? So mathematicians at this point would be saying like, let A and B be two propositions, right? Or fix A and B, or something like this, right? So I can even write it like here. That's what a mathematician would write. Sometimes they don't even write it, it's implicit. Like, of course, when you have a for all, you fix it, you know, or let A and B be arbitrary, often, you know, fixed but arbitrary, or, you know, all these wordings mean the same. And you'll see some examples in the Hitchhiker's Guide. Okay, and then we have A implies B implies A. Well, we can use the same tactic, intros here, to make some progress, to also move A and B among our assumptions. Mathematicians would say here, assume A, assume B, right? So intros in the first case meant fix, or something like that, or let blah be. And intros in the second case means assume, right? So we're just repeating what we have in the logical formula, but in, you know, in kind of mathematical style, so that we can talk about it, right? Because these here are bound variables. We cannot talk about bound variables. It's just a big formula. So we need to open up the formula, and then the goal becomes A, and we have all these things available to prove A, right? In particular, we have A itself, right? It's one of two hypotheses. We've just assumed A, right? And the hypothesis is called HA because that's the name we gave it, right? Mathematicians would often not give names, or would give numbers like 1 in parentheses or 2 in parentheses, right? But we're computer scientists, at least most of us. The survey revealed that there were only 4 mathematicians among us and the vast majority of computer scientists. So we prefer alphanumeric names. And, you know, HA, it means hypothesis A. So usually we'll use H to identify hypothesis. So at this point, we know we have among our hypotheses the goal. So we can just use another tactic, which is called apply, which you know, uses that fact, if you like. So let's see that more slowly. So you see, this is the documentation of intros, which you can read at home. This is the documentation of apply. And again, you have more detailed explanations in the Hitchhiker's Guide. Then you see here a second way of stating the same lemma, well, essentially the same lemma. So here we've said, we have an explicit for all, we have implicit implications, and the first thing we need to do is unpack all of that stuff, right? So that we have it in the context and we have a friendly goal. And then the question is like, why, you know, pack things just to unpack them afterwards? And Lean indeed has a shortcut, which is you can already, when you declare the lemma, put everything unpacked as parameters, right? Before the colon, that's what parameter means. So you declare your A and your B, your HA, your HB in front of a colon, your conclusion is the A, right? So you're saying basically for all A and B, under assumption A and assumption B, you have A. So logically, these two are the same. The first one we had above, and this one are, you know, they're both true or they're both false. We can prove one using the other like easily. But the second one, the unpacked version, is more pleasant to work with, because then we can just write apply HA and we're done. So it's much shorter proof. All right. And now what we see is, well, this is a lot of typing, right? B, E, G, I, N, enter, space, space, blah, 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 enter, E, N, D. And very often we need one-liner proofs. So there's a, you know, there's a syntax for these. It's just by, right? So you just write by like this, by apply HA, right? So you're not forced to use it, but I mean, most people prefer the shorter syntax when it works. Okay, and here, here's another example that's quite, it's quite similar to the example on my whiteboard here. It's a bit different. So I'm going to change my whiteboard just to reflect that change. I like that whiteboard. Let's see. Okay. This is the goal here, right? We first have to declare ABC. And then we have A implies B, which is called HAB. Right? We don't care about the names on the whiteboard. Then we have HBC here. The goal is AC. Having a line in between is always a good idea. This also helps. The little T on the side. And then we see, let's look at the proof state. So of course, this is what I have on the board. And if I advance, you know, past the first command, then you see the first thing I did was to move the hypothesis A among, you know, so the assumption A among my hypothesis here, right? So I said, if I were a mathematician, I would say assume A, right? And then we will prove C. So let's do that. Let's reflect that on the board. Okay, now does that look familiar? Yes, of course. This is exactly the whiteboard I started with earlier. So this is the same example, essentially, you know, apart from the fact that we needed to unpack the A at the beginning, right? And then we can see how it goes. It goes, well, we want to prove C. C is the goal. We have HBC. We use apply. And apply does what we're doing informally on the board. It's like, okay, well, now the C's match, but now I want a B, right? It's this whole trading in a medieval village, right? And then, you know, same thing, HAB, right? We have this A implies B. We know we can use it to prove B, but we're going to have to discharge the condition A. We're going to have to prove A. So we apply HAB, and our new goal is A. And then we look, oh, pattern matching, we have A, so we just apply it. So this is exactly the backward proof that I've shown at the beginning of the lecture. And now there's another related tactic, which is called exact. And exact can be used instead of apply when there's an exact match, right? So apply, you see here at the end, there was an exact match. You know, I have A and A. So I could have used exact, right? So if you don't like exact, you can use apply, and almost always works. There's a small technical difference between the two, which I don't fully understand, so it doesn't really matter. But it's more idiomatic to use exact. It communicates your intentions better. So that's the reason why we also teach it. And finally, but you see, exact is an exact match. It's not this idea of trading, like, oh, well, you can use A implies B to prove B, but then you'll have to give me an A. You cannot use exact in that case. You have to use apply, right? Then you have assumption. So assumption is basically just an exact. that searches among the hypotheses you have, like HA here or HB, if one of them, can just close their goal immediately, right? So this is like mathematicians say this all the time. Well, this follows by assumption, right, or by hypothesis. Well, here's the same thing. So we happen to have a hypothesis that matches exactly, so we can say by assumption. So again, we could live without, we could use exact instead, and we could use apply instead of exact, but these are so basic, so common lean commands that we're covering them. Then another very basic, and I think it's the last time covering in this segment, very basic tactic is REFL, so which is reflexivity. So it's going to prove equations of the form L equals R. Well, I cannot move the cursor over there without getting a tooltip. It proves equations of the form L equals R, where L and R are almost the same thing, except they're equal up to computation. And computation means a whole lot of things in lean, which I'm going to cover just by showing examples. So first of all, so-called alpha renaming, so changing the name of bound variables is an instance of computation. So here we have the same term on both sides, but on one side it talks about X, the other side it talks about Y. Of course, this is completely immaterial, and our friend Refel can do it. And oh, well, this is a one-liner, so we can do it just with by instead if we want. Okay. Then the next example is beta reduction. If you've studied lambda calculus, then you're familiar with it. Beta reduction just means you have a lambda expression here on the left-hand side of an application, and you pass an argument. And at that point, the argument is plugged instead of the bound variable, right? So you end up with a body here, but the X is replaced by A, which is the argument, which is what you have on the right-hand side. So this is, an example of beta reduction, also follows by REFL. Then here we've defined a function double, and well, REFL will even unfold the definition of double to realize that the double of 5 is the same as 5 plus 5. So how about that? And I think it will also unfold the definition of plus, and we can even go all the way to 25, but I'm not sure. And you see, it doesn't work. And this illustrates a very important point about tactics, which is even experts, if I may call myself so, will cannot entirely predict how they will behave, right? They're complicated segments of code that can do all sorts of things, and sometimes you're lucky and it works, and sometimes it doesn't. And the best way to go about them is not to try to think too hard, right? Not think of them more like as being pets or even children, right? They will surprise you once in a while, but I mean, it's just a fact of life. You have to live with it. You shouldn't try to understand a tactic, to the point where you can predict in your head exactly when it will work and when it will not. And when a tactic doesn't work, then you try a different tactic or a different combination, or you break your proof to several steps, which we're going to see in the next lecture. So this is where I usually tell my students, don't panic if you don't understand what the tactic does, because nor do I. I don't know why the tactics do what they do very often, and it doesn't matter. It doesn't prevent me from proving things. So this is where I say, as is written on the back of the Hitchhiker's Guide to the Galaxy, don't panic. So here we have the zeta examples. I mean, you will have fancy names for all these rules. They were probably chosen by Illy. And here, this is a let, right? So let expression. So you can define a name like n here. You say n equals 2 in this expression, right? And then this is 2 plus 2, and this is 4. And of course I could write also 2 plus 2. That would work. And you see, I have no idea where it can do why it can do 2 plus 2 equals 4, but not, maybe 5 plus 5 is not equal 25, maybe it's equal 10. That that's explained it. This is very peinlich. I'm keeping all on tape just to show that to err is human. Eh? But at least the proof assistant cut it. Less fortunately, Zoom also cut it. I'm using Zoom for recording this. Okay, let's continue with the embarrassment. So we have eta, at least I know the names of the Greek letters, so I'm not completely ignorant. 5 plus 5 equals 25, that's a good one. Right, spent too much time at the university, obviously. So eta is when you have, you know, lambda x f of x is a bit redundant, right? You're saying, oh, I am a function that takes x in argument and I return f of x. Then you might just say, I am f, right? This is simpler, right? And indeed, if you beta reduce, then you see that they're the same. You pass an argument a here, then you know you end up with f of a, and if you pass an a here, you also end up with f of a. So just by thinking about how beta reduction works, the eta rule is quite natural, and it holds in lean. And then you have iota, which is about so-called projections. So here we have a pair. So here you have intuitive, a very friendly syntax for pairs. So this doesn't fit in the grammar we had earlier. This is just like the infix operators, like plus don't fit in the grammar of lambda calculus. But this is really, the pair here is really just an object that you know, contains an A and a B. And then you call first on it, and you see Refl can also do that. And that's the end of the segment. So among the tactics I've shown, it's really, I mean, intro and apply will come back again and again and again to haunt you. You'll exact, of course, you can use the other ones. I mean, these are all basic ones, but especially the intro apply is really the absolute essence of tactics. And it's important to develop a good intuition about what they do, because if you're at lecture 5 and you're asking me, you know, what does intro or apply do, then I'm like, okay, I'm sorry, you've missed the train. I'm not sure we can recover from now. So make sure to understand, and if you don't, please ask. Thank you.